Let us now look at an example of this shunt regulator circuit and try to gain more insight into this by putting in some numbers. So let us say that Vi, the unregulated voltage Vi, varies from 9 volts to 13 volts. This is the spec. So this is unregulated Vi, varies from 9 to 13 volts. Then the Zener, let us say the Zener is a 5 volt Zener because we want 5 volt at the output. So we need to take a 5 volt Zener, and let us say the Zener has a spec of 400 milliwatts. What is the range of output R0? So let us try to work it out and find out. So let us say IZ. IZ is the current. What is IZ max? IZ max should be such that the max power dissipation of the Zener 400 milliwatts is not exceeded. So PZ, if I take PZ 400 milliwatts divided by VZ, VZ into IZ is PZ, which is 400 milliwatts by 5 volts. This will give you 80 milliamps. So IZ max or IZ, the current through this branch, should not exceed 80 milliamps. If it exceeds 80 milliamps, then the power dissipation limit of the Zener is crossed and it will blow. So this is one limiting value that you would get, and if you actually plot it on the Zener reverse characteristic, let's say this is Zener's reverse characteristic, this is 5 volts here, and let us say this is the IZ max operating point. This is IZ max, and that is 80 milliamps as calculated like this here. So now RS, let us try to find what is this RS. Vi max, take Vi max, which is 13 volts, minus this node potential, which is Vz, divided by In. Now In, I'll take it as IZ max, assuming that I0 is 0. That is one of the extreme conditions that we saw earlier. So that would be 13 minus 5 divided by 80 milliamps, and which is 100 ohms. So what it means is that under worst case condition, when there is no load, when R0 is infinity, all the current In flows into IZ, and that would be IZ max. Now that current In is maximum when Vi is max. So Vi max minus Vz by IZ max will give you the value of Rs. And what should be the power rating of Rs? So power rating of Rs is given by Vi max minus Vz, that is voltage potential difference across Rs square by the value of Rs, which is 13 minus 5 square by Rs, which is 100, and this turns out to be 0.64 watts. So we have selected Rs. Next, let us look at R0. So first, what is the maximum value of R0, I0 that can be allowed through R0? So I0 max is even under minimum input voltage condition, Vi min minus Vz divided by Rs, will be the IN that flows here under minimum input condition. And at that condition, what is the minimum R0 that you can apply? 9 minus 5 divided by 100, and that is 40 milliamps. That is the maximum I0 that you can allow through the output, and therefore R0 min. If it is max I0, you are talking about R0 min, which is Vz, V0 potential is Vz, divided by I0 max, which is 5 volts divided by 40 milliamps, this one, and that comes to 125 ohms. So therefore, the range of R0 is 125 ohms on one side, on the other side it is open circuit or infinite. So this implies that R0 can take a minimum value of 125 ohms and a maximum value of open circuit. So this is the range of R0 for this particular circuit for this kind of specification. What is the efficiency? You can calculate the efficiency of this to complete the understanding. So efficiency is, we have found out that P0 into RS by VI into delta VIO, or the delta input output differential. Now let us say efficiency max. What is the max efficiency? P0 is max, so we will make P0 max. RS is a fixed value calculated for this particular circuit. VI min, take VI min and delta VIO. When you take VI min, delta VIO will naturally be smaller, minimum of, and therefore the efficiency would be the max possible that you would get. So if you calculate V0 max, which is V0 5 volts into I0 max 40 milliamp into RS, which is 100 ohms, divided by VI min, which is 9 volts, delta VIO, when it is 9 volts and the output is 5 volts, VIO will be 9 minus 5, 4 volts, and this turns out to be 0.55 or 55%. So the efficiency of this circuit for these specifications is 55% at max load condition.